The vastness of space beckons us with its infinite mysteries. Stars scattered across the cosmic canvas, galaxies spiraling into the unknown, and the tantalizing possibility of what lies beyond our reach. Today, we're diving deep into why the cosmic speed limit of 300,000 kilometers per second, the speed of light in vacuum, remains forever beyond our grasp. And I'm curious, where in this beautiful universe are you watching from right now? Drop a comment letting me know your city and what time it is there. It's always fascinating to see how our community spans across different time zones and continents. Now let's begin this journey. That's an incredible amount of power, but just to survive the journey, adding mass and exacerbating the energy problem we discussed earlier. The cosmic microwave background, the faint afterglow of the Big Bang that permeates all of space, would also become a hazard. At rest, this radiation is harmless, with a temperature of just 2.7 Kelvin above absolute zero. But at relativistic speeds, it would be blue-shifted into high-energy gamma rays bombarding your spacecraft from the direction of travel. Navigation presents another challenge. At speeds approaching light, your ability to react to obstacles becomes severely limited. If your sensors detect a small asteroid 10,000 kilometers ahead, at 99% of light speed, you'd have just 33 milliseconds to react before impact. That's barely enough time for a signal to travel from your sensors to your computer, let alone to calculate and execute an evasive maneuver. Communication with Earth would become increasingly difficult as well. Radio signals traveling at light speed would take years to reach home, and years more for a response to return. Any mission approaching light speed would necessarily be autonomous, cut off from real-time guidance or assistance. The psychological effects of such isolation can't be overlooked. Humans are social creatures, evolved for life in groups and communities. The profound isolation of interstellar travel, combined with the knowledge that everyone and everything you've ever known is aging rapidly compared to you, would create psychological stresses we can barely comprehend. Some have suggested that suspended animation or generation ships might offer solutions to these problems. But these approaches don't solve the fundamental physics. They merely attempt to work around the human limitations. And they come with their own enormous technical and ethical challenges. The relativistic rocket equation, which extends the classical rocket equation to account for relativistic effects, paints an even bleaker picture than the classical version. As your spacecraft approaches light speed, the effective mass of your fuel increases along with your own mass, creating a compounding problem that makes the energy requirements grow exponentially. Let's push deeper into the theoretical barriers that make light speed travel an impossibility rather than just an engineering challenge. Einstein's special relativity gives us a mathematical relationship between energy, mass, and velocity that becomes particularly revealing as we approach light speed. The famous equation E equals mc squared is actually a special case of a more general formula. E equals gamma mc superscript 2, where gamma is the Lorentz factor. This Lorentz factor equals 1 divided by the square root of 1 minus v superscript 2 divided by c superscript 2, where v is your velocity and c is the speed of light. As your velocity approaches the speed of light, this denominator approaches zero, causing the Lorentz factor to approach infinity. What does this mean in practical terms? As you accelerate toward light speed, your relativistic mass increases without bound. At 90% of light speed, your mass is already more than double your rest mass. Consider a thought experiment. If you could send information faster than light, you could, in principle, send a message to your past self. This violates causality and creates a logical contradiction. The universe appears to be structured specifically to prevent such paradoxes, with the light speed limit serving as a cosmic safeguard. Quantum entanglement might seem to offer a loophole. When two particles are entangled, measuring one instantly affects the other, regardless of the distance between them. This spooky action at a distance, as Einstein called it, appears to transmit information faster than light. But deeper analysis reveals that no actual information is transmitted through entanglement. You cannot use entangled particles to send a message faster than light. The correlation between measurements is real, but it cannot be used to transmit information, preserving the cosmic speed limit. The unification of quantum mechanics and general relativity, a still unsolved problem in theoretical physics, might someday reveal new insights about the nature of space-time. But every attempt at such unification so far has preserved the light speed limit rather than undermining it. String theory, loop quantum gravity, causal set theory, all these approaches to quantum gravity maintain the primacy of the speed of light as a universal constant. If anything, they suggest that space-time itself may be discrete at the smallest scales, which would make the light speed limit even more fundamental than we currently understand. Some have suggested that perhaps the constants of nature, including the speed of light, might vary in different regions of the universe or have changed over cosmic time. But observational evidence strongly constrains such variations. Spectroscopic analysis of distant galaxies shows that the fine structure constant, which incorporates the speed of light, has remained constant to within a few parts per million over billions of years. The Michelson-Morley experiment in 1887 famously failed to detect the luminiferous ether through which light was thought to propagate. This null result eventually led to Einstein's special relativity and the understanding that the speed of light is constant for all observers. More than a century of increasingly precise experiments have confirmed this principle to extraordinary accuracy. Let's delve deeper into the energy requirements that make light's speed travel so prohibitive, examining both theoretical limits and practical considerations that constrain our cosmic ambitions. The relativistic rocket equation gives us a mathematical framework for understanding just how daunting the energy requirements become as we approach light speed. Unlike the classical rocket equation, which describes how much propellant is needed to achieve a given change in velocity, the relativistic version accounts for the increase in effective mass as velocity increases. For a rocket with an exhaust velocity of 10% of light speed, far beyond our current capabilities, achieving 90% of light speed would require a mass ratio, initial mass divided by final mass, of about 13,000. This means that for every kilogram of payload and structure, you'd need 13,000 kilograms of propellant. For a modest spacecraft weighing 10 metric tons, you'd need 130,000 metric tons of propellant, roughly equivalent to the mass of an entire aircraft carrier. Push the target velocity to 99% of light speed, and the mass ratio skyrockets to more than 2 million. At 99.9%, it exceeds 2 billion. These numbers quickly become so large as to be meaningless in any practical sense. Even antimatter, the most energy-dense fuel theoretically available to us, cannot escape these mathematical realities. While matter-antimatter annihilation converts mass to energy with perfect efficiency, the rocket still needs to carry both the matter and antimatter components of the fuel, and the mass ratios required by the relativistic rocket equation still apply. The total energy contained in 1 kilogram of matter-antimatter fuel is equivalent to 43 megatons of TNT. That's an enormous amount of energy, roughly 3,000 times the yield of the bomb dropped on Hiroshima. But even this incredible energy density falls far short of what would be needed for practical interstellar travel at relativistic speeds. Consider the energy requirements from another perspective. The kinetic energy of an object increases with velocity according to the relativistic formula. Ke equals gamma 1, mc superscript 2. At 90% of light speed, the kinetic energy is 1.3 times the rest mass energy. At 99%, it's 6 times the rest mass energy. At 99.9%, it's 21 times the rest mass energy. For a spacecraft with a mass of 10 metric tons, reaching 99% of light speed would require an energy input equivalent to converting 60 metric tons of matter entirely to energy. That's 6 times the mass of the spacecraft itself, converted with perfect efficiency, something we have no idea how to achieve. To put these energy requirements in perspective, the total annual energy consumption of human civilization is currently about 600 exajoules, or about 6.6 trillion kilowatt-hours. Accelerating our hypothetical 10-ton spacecraft to 99% of light speed would require more than 500 times this amount, 3,000 exajoules, or the total energy consumption of human civilization for 5 centuries. And this is just the energy needed for acceleration. A practical interstellar mission would also need energy for deceleration at the destination, life support during the journey, and various other systems. The total energy budget quickly becomes astronomical in the most literal sense. Current propulsion technologies fall woefully short of what would be needed for relativistic travel. Chemical rockets, like those that took humans to the moon, have specific impulses, a measure of efficiency, of around 400 seconds. This corresponds to an exhaust velocity of just 3.9 kilometers per second or about 0.00013 times the speed of light. Ion thrusters, which use electrical fields to accelerate charged particles, achieve higher specific impulses, up to 5,000 seconds in current designs. But that's still just 0.00017 times the speed of light. And ion thrusters produce very low thrust, meaning acceleration is extremely gradual. Nuclear thermal rockets, which use nuclear reactions to heat propellant, could potentially achieve specific impulses of around 900 seconds, better than chemical rockets, but still far too low for relativistic travel. Nuclear pulse propulsion, as envisioned in Project Orion, would use a series of nuclear explosions to push a spacecraft. This could theoretically achieve a specific impulse of about 30,000 seconds, or 1% of light speed. But the engineering challenges, not to mention the political and environmental concerns, make this approach highly problematic. Fusion rockets remain theoretical, but could potentially achieve specific impulses of 1 million seconds or more, about 3% of light speed. Even with such technology, which remains beyond our current capabilities, the mass ratios required for relativistic travel would still be prohibitive. Beamed propulsion concepts, like those proposed by Breakthrough Starshot, attempt to sidestep the rocket equation by leaving the power source behind. By using ground-based or space-based lasers to push light sails, these approaches could potentially accelerate small payloads to significant fractions of light speed without carrying fuel. But even these concepts face enormous engineering challenges. The Breakthrough Starshot proposal aims to accelerate gram-scale star chips to 20% of light speed using a 100-gigawatt laser array, a power level equivalent to about 100 nuclear power plants. Scaling this up to accelerate a crewed spacecraft would require power levels far beyond anything we can currently produce or direct. The interstellar medium presents another energy challenge. At relativistic speeds, each hydrogen atom encountered becomes a high-energy particle capable of causing significant damage. A spacecraft traveling at 99% of light speed through the interstellar medium, with its typical density of 1 atom per cubic centimeter, would encounter these atoms as if they were cosmic rays with energies of several giga-electron volts. The resulting radiation would not only damage electronics and structural materials, but would also pose a severe health hazard to any crew. Shielding against this radiation would require substantial mass, further exacerbating the energy requirements for acceleration. Some have proposed using magnetic fields to deflect charged particles, creating a sort of magnetic shield around the spacecraft. But generating magnetic fields strong enough to deflect relativistic particles would require enormous amounts of energy itself, creating a compounding problem. Interstellar dust presents an even more serious hazard. While the interstellar medium contains only about 1 dust grain per cubic kilometer, each impact at relativistic speeds would release energy equivalent to small nuclear explosions. A single dust grain with a mass of just 1 microgram would impact with the energy of about 200 kilograms of TNT at 99% of light speed. No known material could withstand such impacts. Whipple shields, layered barriers designed to break up impactors, might offer some protection against the smallest particles, but would be ineffective against larger dust grains. And adding more shielding means more mass, which means even more energy required for acceleration. The braking problem is often overlooked in discussions of interstellar travel. Even if we somehow solved all the problems associated with acceleration to relativistic speeds, we'd still need to decelerate at the destination. This would require either carrying fuel for the deceleration burn, doubling the already impossible fuel requirements, or some method of using the target star system for braking, such as magnetic sails or gravitational assists. Magnetic sails would use the stellar wind of the target star to generate drag, gradually slowing the spacecraft. But this would require enormous magnetic fields and would result in very gradual deceleration, potentially taking decades to complete. Gravitational assists could help, but would require precise navigation and would still need to be combined with other braking methods. Some have suggested using antimatter for the deceleration burn, since it has the highest possible energy density. But this would require carrying the antimatter safely for the entire journey and developing containment systems that could survive the harsh conditions of relativistic travel. The energy storage problem is equally daunting. Even if we could generate the enormous amounts of energy needed for relativistic travel, storing that energy in a form that could be used for propulsion presents its own challenges. Batteries, capacitors, and other conventional energy storage technologies have energy densities far too low for interstellar applications. Beyond the formidable physical and engineering barriers to light-speed travel, we must also consider the human element. If we somehow overcame the theoretical obstacles, what would relativistic space travel mean for the human beings undertaking such journeys? The biological effects of long-duration spaceflight are already challenging enough at conventional speeds. Studies of astronauts who spent extended periods on the International Space Station have revealed concerning changes to human physiology and microgravity, muscle atrophy, bone density loss, cardiovascular deconditioning, immune system suppression, and vision problems, among others. Scott Kelly's year-long mission on the ISS, completed in 2016, provided valuable data on these effects. Despite rigorous exercise regimens and medical interventions, he experienced significant physiological changes, including alterations to his gene expression that persisted after his return to Earth. And this was just from 1 year in space, far shorter than any potential interstellar journey. A mission to even the nearest star system at a significant fraction of light speed would take years from the crew's perspective, even with relativistic time dilation. The physiological challenges would be immense, potentially requiring artificial gravity systems to mitigate the effects of prolonged weightlessness. Rotating habitats could theoretically provide artificial gravity through centripetal force, but these would need to be quite large to avoid problems with the Coriolis effect, which causes disorientation when the rotation rate is too high. A habitat with a radius of 50 meters would need to complete one rotation every 20 seconds to simulate Earth gravity, creating significant engineering challenges for structural integrity. Radiation exposure represents an even more serious health concern for interstellar travelers. Beyond the protection of Earth's magnetic field and atmosphere, astronauts are exposed to cosmic radiation that can damage DNA and increase cancer risk. Current estimates suggest that a mission to Mars would expose astronauts to radiation doses approaching or exceeding NASA's career limits. For an interstellar mission, the radiation exposure would be orders of magnitude greater. Galactic cosmic rays, high-energy particles accelerated by distant supernovae and other cosmic events, would bombard the spacecraft continuously. And as we discussed earlier, at relativistic speeds, even the normally harmless interstellar medium becomes a source of dangerous radiation. Shielding against this radiation would require either enormous amounts of mass, further increasing the energy requirements, or advanced active shielding technologies that remain theoretical. Some have proposed using superconducting magnetic fields to deflect charged particles, but generating fields strong enough to protect against relativistic particles would require enormous amounts of energy. Water makes an excellent radiation shield due to its hydrogen content, but the quantities needed for effective shielding would be substantial. A water shield just 10 centimeters thick around a modest habitat module would weigh dozens of tons, mass that would need to be accelerated and decelerated, multiplying the energy requirements. The psychological challenges of interstellar travel might prove even more daunting than the physiological ones. Humans evolved in social groups with access to diverse environments and stimuli. The profound isolation and confinement of an interstellar journey would create psychological stresses unlike anything experienced in human history. Studies of isolated groups in analogous environments, Antarctic research stations, submarine crews, participants in isolation experiments like Mars 500, have documented increased rates of depression, anxiety, sleep disorders, and interpersonal conflicts. And these situations still allowed for real-time communication with the outside world and the knowledge that help was available if needed. Interstellar travelers would face isolation of an entirely different magnitude. As they moved away from Earth at relativistic speeds, communications would be subject to increasing time delays. Eventually, meaningful two-way communication would become impossible. The psychological impact of being truly cut off from humanity, potentially for the remainder of one's life, cannot be overstated. The time dilation effects of relativistic travel create another layer of psychological complexity. As the spacecraft approached light speed, time would pass more slowly for the crew than for those left behind on Earth. A journey that took 10 years from the crew's perspective might correspond to decades or centuries of Earth time, depending on the velocity. This means that interstellar travelers would effectively be journeying not just through space, but through time as well. If they ever returned to Earth, they would find a world transformed, perhaps unrecognizably so. Everyone they knew might be long dead. The culture, technology, and perhaps even the language might have evolved beyond their recognition. This one-way journey through time creates profound ethical questions. Is it right to send humans on missions from which they can never truly return home? How would the knowledge that everyone and everything they left behind is aging rapidly affect the psychological well-being of the crew? Some have suggested that these challenges might be addressed through various forms of suspended animation or hibernation. If crew members could be placed in a state of metabolic suppression for the duration of the journey, they might avoid both the psychological strain of isolation and the physiological effects of long-duration spaceflight. Current medical technology allows for therapeutic hypothermia, cooling the human body by a few degrees to reduce metabolic rate and protect tissues during certain medical emergencies. But true suspended animation, reducing metabolism to near zero for years at a time, remains firmly in the realm of science fiction. Cryonics, the freezing of human bodies or brains in the hope of future revival, faces fundamental challenges related to ice crystal formation, which damages cells at the microscopic level. Vitrification techniques using cryoprotectants can prevent ice formation, but introduce their own toxicity issues. And no one has yet demonstrated the revival of a complex organism after long-term cryopreservation. The generational ship concept sidesteps some of these issues by accepting that the original crew will not live to see the destination. Instead, their descendants would complete the journey, having been born and raised entirely in the artificial environment of the spacecraft. This approach creates its own ethical and practical challenges. The children born on such a mission would have no choice in their participation. They would be committed to a life within the confines of the spacecraft, never experiencing the open skies, diverse ecosystems, or cultural richness of Earth. Maintaining genetic diversity would be a significant challenge for a generational ship. Studies suggest that a minimum population of several thousand individuals would be needed to avoid dangerous levels of inbreeding over multiple generations. This would require a much larger spacecraft, further increasing the already prohibitive energy requirements. Social stability over multiple generations cannot be guaranteed. Historical examples of isolated communities show that cultural drift, factional conflicts, and even the loss of technological knowledge can occur over time. There's no assurance that the descendants of the original crew would maintain the mission objectives or even the technical skills needed to operate the spacecraft. Some have suggested that artificial intelligence and robotics might offer solutions to these human limitations. Perhaps we could send robotic probes instead of human crews, avoiding the biological and psychological challenges altogether. But current AI systems, despite their impressive capabilities in specific domains, lack the general intelligence, adaptability, and problem-solving abilities that would be needed for autonomous interstellar exploration. They cannot match the human ability to respond creatively to unexpected situations or to make value judgments about what is worth investigating. More advanced AI systems might eventually overcome these limitations, but then we face philosophical questions about the purpose of exploration. If we develop AI sophisticated enough to fully replace human explorers, would sending such entities to the stars satisfy our desire for exploration? Would their discoveries and experiences meaningfully extend human knowledge and presence into the cosmos? The development of brain-computer interfaces and mind-uploading technologies has led some futurists to propose more radical solutions. Perhaps human consciousness could be transferred to synthetic substrates that wouldn't face the same biological limitations as organic bodies. Such post-biological entities might be better suited to the harsh conditions of interstellar space and the extreme timescales of interstellar travel. They might not require life support systems, could potentially be more radiation-resistant, and might even operate on timescales that make the long journey seem subjectively shorter. But these technologies remain highly speculative. We have no scientific consensus on whether consciousness could be transferred to a different substrate, or even a complete theory of how consciousness arises from neural activity in the first place. And such approaches raise profound questions about identity, continuity of self, and what it means to be human. To truly understand the challenge of light-speed travel, we need to zoom out and consider our place in the cosmic context. The scale of the universe, both in space and time, provides important perspective on our interstellar ambitions. Our Milky Way galaxy spans 100,000 light-years from edge to edge, containing somewhere between 100 billion and 400 billion stars. Even if we could somehow achieve 99% of light speed, crossing our galaxy would still take over 100,000 years. And the Milky Way is just one of perhaps 2 trillion galaxies in the observable universe. The cosmic calendar, popularized by Carl Sagan, helps us visualize the immensity of cosmic time by compressing the 13.8 billion-year history of the universe into a single year. On this scale, where each month represents about 1.1 billion years, human civilization appears only in the last few seconds before midnight on December 31st. Our species has existed for only about 300,000 years, a cosmic eye blink. Modern technological civilization is younger still, perhaps 5,000 years if we're being generous. The scientific revolution that gave us our current understanding of physics is barely 400 years old. And our first tentative steps into space began just 64 years ago with the launch of Sputnik. Given this perspective, it seems almost absurdly presumptuous to declare that we will never reach light speed. After all, couldn't future technologies, developed over thousands or millions of years, eventually overcome the barriers we currently face? This is a fair question, and humility about the limits of our current knowledge is certainly warranted. Throughout history, many seemingly impossible feats have eventually been achieved through technological advancement. But the light speed barrier appears to be of a different nature than previous technological hurdles. The impossibility of faster-than-light travel isn't merely a limitation of our current technology or engineering capabilities. It's woven into the fundamental structure of space-time as we understand it. Einstein's theories of relativity have been tested with extraordinary precision for over a century, and every experiment has confirmed their predictions. The Global Positioning System, GPS, that guides our smartphones relies on relativistic corrections to function accurately. Particle accelerators routinely accelerate subatomic particles to 99.99999% of light speed, observing precisely the mass increase and time dilation effects predicted by special relativity. Gravitational waves, detected for the first time in 2015 by LIGO, behave exactly as general relativity predicts. Given this overwhelming experimental confirmation, it seems unlikely that relativity's prohibition on faster-than-light travel is simply a mistake or an approximation that will eventually be overturned. More likely, it represents a fundamental constraint of our universe, as basic and immutable as the conservation of energy or the second law of thermodynamics. That said, science remains open to revision based on new evidence. If observations were made that contradicted relativity's predictions, physicists would certainly investigate and potentially revise our theories. But after more than a century of increasingly precise tests, no such contradictions have been found. Some have suggested that quantum mechanics might eventually provide loopholes in relativistic prohibitions. After all, quantum phenomena like entanglement seem to operate instantaneously across any distance, apparently violating locality. But deeper analysis shows that even quantum entanglement cannot transmit information faster than light. The no-communication theorem in quantum mechanics proves mathematically that the correlations observed in entangled particles cannot be used to send signals. Quantum teleportation, despite its name, still requires classical information transmitted at light speed or below to complete the process. The unification of quantum mechanics and general they would never live to see the finished structure. Yet they began the work anyway. Miniaturized, unmanned probes rather than human missions, it sidesteps many of the most challenging aspects of interstellar travel while still potentially allowing us to study nearby star systems directly. Even at 20% of light speed, these probes would take about 20 years to reach Alpha Centauri. Add the 4.3 years for the data to be transmitted back to Earth, and the total mission time approaches a quarter century, still within a human lifetime, but just barely. Scaling up such technology to accommodate human passengers would increase the energy requirements by many orders of magnitude, pushing the mission timeline well beyond a human lifespan even with the most optimistic projections. This suggests that robotic exploration may be our only practical path to the stars, at least in the near term. But even robotic exploration faces enormous challenges. The interstellar medium, while incredibly diffuse by earthly standards, becomes a serious hazard at relativistic speeds. A single dust grain could disable or destroy a spacecraft traveling at a significant fraction of light speed. Shielding against such impacts would add mass, reducing the achievable velocity and increasing the journey time. Communication across interstellar distances presents another challenge. Radio signals weaken with the square of the distance, meaning that a probe at Alpha Centauri would need to transmit with enormous power to be detectable on Earth. And the bandwidth would be severely limited, restricting the amount of data that could be sent back. Laser communication could potentially offer higher bandwidth, but would require precise pointing over interstellar distances, a formidable technical challenge. And regardless of the communication method, the speed of light delay would make any form of real-time control impossible. Interstellar probes would necessarily be autonomous, making their own decisions about what to observe and study. The development of artificial general intelligence might eventually provide a solution to these challenges. A sufficiently advanced AI could potentially serve as a proxy for human exploration, making the kinds of value judgments and creative decisions that currently require human intelligence. But this raises philosophical questions about the purpose of exploration. If we develop AI sophisticated enough to fully replace human explorers, would sending such entities to the stars satisfy our desire for exploration? Would their discoveries and experiences meaningfully extend human knowledge and presence into the cosmos? Given the seemingly insurmountable barriers to light-speed travel, perhaps we should consider alternative approaches to exploring and understanding our cosmic environment. These alternatives might not offer the romantic appeal of starships cruising between the stars, but they could provide practical paths to expanding our cosmic horizons. Advanced telescopes represent our most immediate and practical tool for studying the universe beyond our solar system. The James Webb Space Telescope, launched in December 2021, offers unprecedented capabilities for observing distant stars and exoplanets, millions of stars across a wide range of frequencies. If successful, SETI could provide not just confirmation that we are not alone in the universe, but potentially access to the scientific and cultural knowledge of more advanced civilizations. This would represent a form of cosmic exploration by proxy, allowing us to learn about the universe through the observations and discoveries of others. Active SETI, or METI, messaging to extraterrestrial intelligence, takes this concept a step further by deliberately sending signals to potentially habitable exoplanets. While controversial due to concerns about revealing our presence to unknown civilizations, METI could potentially establish two-way communication with extraterrestrial intelligence, creating a form of interstellar dialogue that would not require physical travel. Of course, such communication would still be limited by the speed of light. A conversation with a civilization even around the nearest star would have a minimum round-trip time of 8.6 years. But over decades or centuries, a meaningful exchange of information could occur, potentially providing insights about the universe from perspectives very different from our own. Virtual exploration represents yet another alternative to physical interstellar travel. As our computational capabilities advance, we may eventually be able to create detailed simulations of other star systems based on telescopic observations. These simulations would allow a form of virtual presence, enabling scientists and perhaps eventually the public to experience alien environments without leaving Earth. Such simulations would necessarily involve extrapolation beyond the available data, but they could still provide valuable insights and testable hypotheses about exoplanetary environments. And as our observational data improved, the simulations could be refined to more accurately reflect reality. The development of advanced brain-computer interfaces might eventually allow for truly immersive virtual exploration, creating experiences subjectively indistinguishable from physical presence. While such technology remains speculative, it could potentially satisfy much of the human desire for exploration without requiring the enormous energy expenditures of interstellar travel. Some futurists have proposed even more radical approaches to cosmic exploration. The concept of mind uploading, transferring human consciousness to synthetic substrates, has been suggested as a potential solution to the challenges of interstellar travel. Digital minds would not require life support systems, could potentially be more radiation resistant, and might operate on timescales that make the long journey seem subjectively shorter. Such post-biological entities might be better suited to the harsh conditions of interstellar space, and the extreme timescales of interstellar travel. They could potentially be transmitted as information at the speed of light, allowing a form of interstellar travel limited only by the availability of receiving stations at the destination. But these technologies remain highly speculative. We have no scientific consensus on whether consciousness could be transferred to a different substrate, or even a complete theory of how consciousness arises from neural activity in the first place. And such approaches raise profound questions about identity, continuity of self, and what it means to be human. A more near-term approach might be the development of self-replicating probes, sometimes called von Neumann probes after the mathematician John von Neumann, who first described the concept of self-replicating machines. Such probes would be designed to travel to a star system, use local resources to build copies of themselves, and then send these copies to other star systems. This approach could potentially allow exploration of the entire galaxy within a few million years, even with subrelativistic travel speeds. Each probe would only need to reach the nearest star systems, with subsequent generations extending the reach of exploration ever further. The technical challenges would be enormous, requiring advanced robotics, artificial intelligence, and manufacturing capabilities far beyond our current technology. And there would be serious ethical concerns about releasing self-replicating machines into the galaxy, particularly if they consumed significant resources from the systems they visited. But the concept illustrates an important point. With sufficient patience and a willingness to think beyond individual human lifespans, the limitations imposed by the light speed barrier become less prohibitive. We might not be able to personally visit the stars in a single human lifetime, but humanity as a whole could potentially explore the galaxy over longer timescales. This brings us to perhaps the most profound alternative to light speed travel, extending our perspective beyond the individual human lifespan. If we could develop technologies to dramatically extend human longevity, perhaps eventually achieving indefinite lifespans, the time constraints of interstellar travel would become less prohibitive. A journey of centuries or even millennia might be acceptable if one could reasonably expect to live that long. The biological and medical challenges of radical life extension are enormous, but perhaps no more so than the physics and engineering challenges of faster-than-light travel. Even without such radical life extension, we might develop social and institutional structures that allow for meaningful participation in multi-generational projects. The Long Now Foundation, mentioned earlier, represents an early attempt to foster thinking and planning on timescales of centuries or millennia rather than years or decades. Religious institutions have demonstrated the ability to maintain continuity of purpose over many centuries. The Catholic Church has existed as a continuous organization for nearly 2,000 years. Some Japanese temples have been maintained by successive generations of caretakers for over a millennium. These examples suggest that human institutions can persist and maintain focus over timescales relevant to interstellar exploration. Perhaps the most realistic approach to becoming a truly cosmic species involves a combination of these alternatives: advanced telescopes and virtual exploration in the near term, robotic probes and possibly self-replicating systems in the medium term, and gradual, multi-generational expansion at subrelativistic speeds in the long term. This more patient approach lacks the dramatic appeal of faster-than-light starships, but it aligns with the physical realities of our universe as we currently understand them. And it offers a path forward that doesn't require overturning fundamental physics or achieving engineering feats that may be literally impossible. The philosopher and mathematician Bertrand Russell once wrote, "There is darkness without, and when I die there will be darkness within. There is no splendor, no vastness anywhere, only triviality for a moment, and then nothing." This bleak assessment reflects a common human fear, that the vastness of the cosmos, combined with our own limitations, renders our existence ultimately meaningless. But perhaps the light speed limit, rather than being merely a frustrating barrier to our cosmic ambitions, offers a different perspective. The fact that we cannot easily reach the stars means that our home, this pale blue dot in the cosmic ocean, takes on greater significance. If we cannot simply move on to new worlds when we've exhausted this one, then the preservation and flourishing of Earth and its biosphere becomes not just desirable, but essential. The light speed limit might be seen as a kind of cosmic incentive for sustainability, encouraging us to value and protect the extraordinary planet that gave rise to us. Rather than racing outward to the stars, perhaps we should focus first on becoming better stewards of our home world and developing the wisdom and patience that would make us worthy of cosmic citizenship. This doesn't mean abandoning the dream of reaching the stars, only approaching it with greater humility and a longer perspective. The universe has existed for nearly 14 billion years and will likely continue for trillions more. Our species is young, barely 300,000 years old. We have time to grow, to learn, to develop the technologies and wisdom needed for sustainable cosmic expansion. The physicist Freeman Dyson once suggested that the universe is not only queerer than we suppose, but queerer than we can suppose. Perhaps the ultimate solution to the light speed problem will come from directions we cannot currently imagine, from discoveries in physics or biology or computing that open new pathways to the stars. But until such discoveries are made, if they ever are, we would do well to accept the light speed limit not as a frustrating barrier, but as a fundamental feature of our universe, one that shapes the character and trajectory of any technological civilization that arises within it. The light speed barrier raises profound philosophical questions about humanity's place in the cosmos and the nature of our future as a species. These questions extend far beyond the technical challenges we've discussed, touching on issues of purpose, meaning, and the ultimate destiny of intelligent life. The Fermi paradox, the apparent contradiction between the high probability of extraterrestrial civilizations and the lack of evidence for their existence, takes on new significance when we consider the light speed barrier. If faster-than-light travel is truly impossible, then the colonization of the galaxy would necessarily be a slow process, potentially explaining why we don't see evidence of alien civilizations despite the billions of potentially habitable planets in our galaxy. Physicist Michael Hart and others have argued that even at modest sublight speeds, a technological civilization could colonize the entire Milky Way within a few million years, a mere eye blink in cosmic time. The fact that this apparently hasn't happened might suggest that technological civilizations are exceedingly rare, tend to destroy themselves before achieving interstellar capability, or choose not to expand for reasons we don't yet understand. The light speed limit might contribute to this explanation. If interstellar travel is as difficult and resource-intensive as our current understanding of physics suggests, perhaps most civilizations choose to focus their energies inward rather than outward, developing virtual realities, artificial intelligence, or other technologies that don't require overcoming the enormous challenges of interstellar travel. Or perhaps the vastness of space and the light speed limit create a natural quarantine, preventing civilizations from interfering with each other's development until they've reached a certain level of maturity. This concept, sometimes called the cosmic quarantine hypothesis, suggests that the apparent emptiness of our cosmic neighborhood might be a feature rather than a bug, allowing each technological species to develop according to its own trajectory before encountering others. The philosopher Nick Bostrom has proposed the simulation hypothesis, the idea that our Benford has suggested that advanced civilizations might communicate primarily through galactic internet protocols, transmitting information rather than physical objects between star systems. In this scenario, the light speed limit would constrain the speed of communication but not necessarily prevent meaningful interaction between civilizations. Over time, such a network might develop into what Carl Sagan called a galactic library, a repository of knowledge and experience from thousands or millions of different intelligent species. Participation in such a network might offer far more value than physical travel between stars, particularly if the network included virtual environments that could be experienced subjectively. The concept of transcension, proposed by futurist John Smart, suggests that advanced civilizations might naturally evolve toward increasingly dense, efficient states of organization, eventually disappearing from observable space into black hole-like structures that maximize computational efficiency. In this scenario, the apparent emptiness of the cosmos might reflect not the absence of advanced intelligence, but its evolution toward forms we cannot yet recognize or detect. These speculative scenarios highlight a crucial point. The light speed limit doesn't necessarily prevent the expansion of intelligence or consciousness throughout the cosmos. It merely constrains the form that such expansion might take, potentially channeling it toward modes of existence very different from our current physical embodiment. The philosopher Hans Moravec has suggested that the ultimate destiny of intelligence might be to transform the entire universe into what he calls mind fire, substrate optimized for computation and experience. In this scenario, the physical exploration of space becomes merely a preliminary step toward a much more profound transformation of matter and energy into forms optimized for intelligence. Such speculation might seem to stray far from our original question about the feasibility of light-speed travel. But it illustrates an important point. Perhaps the question itself reflects a limited perspective, focusing on the constraints of our current physical form rather than the broader possibilities for the evolution of intelligence and consciousness. The light speed limit, in this view, isn't merely a frustrating barrier to our cosmic ambitions. It's a fundamental feature of our universe that shapes the evolutionary trajectory of all technological civilizations, potentially channeling them toward modes of existence very different from our current physical embodiment. This perspective offers a kind of cosmic optimism in the face of the light speed barrier. Perhaps we don't need to break the light speed limit to fulfill our destiny as an intelligent species. Perhaps our true potential lies in directions we can barely imagine from our current perspective, in the development of artificial intelligence, virtual realities, or forms of consciousness that transcend our biological limitations. The philosopher and cognitive scientist David Chalmers has suggested that virtual realities could eventually become as real, subjectively indistinguishable from physical reality, and potentially offering experiences far richer and more diverse than those available in our physical universe. If this is true, perhaps the most valuable exploration isn't outward to the stars, but inward to increasingly sophisticated virtual environments. This doesn't mean abandoning the dream of reaching the stars, only recognizing that our cosmic destiny might involve transformations far more profound than merely extending our current physical form into space. The light speed limit constrains one particular mode of expansion, but it doesn't necessarily limit the ultimate potential of intelligence and consciousness to permeate and transform the cosmos. The physicist Freeman Dyson once speculated about the ultimate fate of intelligence in a universe subject to heat death, the eventual dissipation of all usable energy as the universe expands and cools. He suggested that even in such a universe, intelligence might survive indefinitely by thinking ever more slowly as available energy decreases, potentially experiencing an infinite subjective time in a finite objective time. This kind of long-term thinking reminds us that the true constraints on our cosmic potential might not be the light speed limit, but rather the fundamental thermodynamic limits of computation and experience in an expanding universe. Compared to these ultimate constraints, the inability to travel faster than light might seem a relatively minor limitation. The philosopher and futurist Nick Bostrom has argued that the development of artificial general intelligence might represent a more significant transformation in our cosmic potential than interstellar travel. If we create artificial intelligence that surpasses human capabilities, such entities might develop technologies or insights that open entirely new pathways for cosmic expansion, perhaps including solutions to the light speed problem that we cannot currently imagine. This perspective suggests that our focus on the light speed barrier might reflect a kind of present bias, an assumption that the constraints of our current understanding are permanent rather than temporary. Throughout history, seemingly insurmountable barriers have often yielded to new insights or approaches that weren't visible from earlier perspectives. That said, the light speed limit appears to be of a different nature than previous technological hurdles. It's not merely a practical limitation, but a fundamental feature of space-time as we understand it. While we should remain open to the possibility of new physics that might change our understanding, we should also be prepared for the possibility that this particular constraint is indeed permanent. If so, perhaps the wisest approach is to accept this constraint and work within it, developing technologies and social structures that allow for meaningful cosmic expansion even at sublight speeds. This might include advanced propulsion systems that can achieve a significant fraction of light speed, suspended animation technologies that allow humans to survive long journeys, or social institutions that can maintain continuity of purpose over many generations. It might also include the development of artificial intelligence, virtual reality, and other technologies that expand our effective reach beyond the limitations of our biological bodies. If we cannot physically travel to distant stars within a human lifetime, perhaps we can send our artificial emissaries, experiencing alien environments through their sensors, and potentially establishing communication with other intelligent beings. The philosopher and cognitive scientist Daniel Dennett has suggested that human consciousness itself might be understood as a kind of virtual machine running on the hardware of our brains. If this view is correct, perhaps the distinction between physical and virtual exploration is less fundamental than it might initially appear. Our experience of the physical world is already mediated through our senses and cognitive processes, a kind of virtual reality generated by our brains. This perspective suggests that the development of increasingly sophisticated virtual realities might represent not a retreat from exploration, but an extension of our natural cognitive processes, allowing us to experience environments and phenomena that would otherwise be inaccessible due to physical or temporal constraints. The light speed barrier, in this view, doesn't prevent us from experiencing the cosmos. It merely constrains the particular form that such experience might take. And perhaps this constraint isn't as limiting as it might initially appear, given the vast potential for expanding our experience through technology. If you made it this far, make sure to subscribe to the channel and give a like. Also, I am sure you will love this other video at the left side of the screen. Is the speed of light really the fastest speed in the universe? In this video, we explore the science behind the speed of light limit, from superluminal jets and quantum entanglement to cosmic inflation, wormholes, and much more.